Analyzing traffic provides some fascinating data, doesn't it? We've seen it with Mike, and we're about to see another angle from our next speaker, who is a security specialist at Adjust, and he'll join us on stage in just a few seconds to show us how a popular app with over 10 million downloads can steal mobile traffic. Abdullah Obayed, welcome to DefCamp. Let's give Abdullah a big round of applause.
Hello. Everybody can hear me?
Yep.
Yay. All right, so stealing traffic. Hi. And the screen is out, so. Oh, it's not. It's just out in here. Okay, no worries. So, my name is Abdullah. I work at a mobile attribution provider company called Adjust. And mobile attribution is basically how people can, how advertisers can find and locate the people who have installed their apps and know which network provided that, and from there they can they use our technology so that they can find the attribution. So I work in there as a security analyst, former software engineer, and I work in their fraud team. Well, it's mispronounced. It should be the anti-fraud team, but whatever. So, yeah. So, first of all, before we go on to the presentation, mobile attribution is kind of a big deal. Right now, we receive 1 petabyte per day data through our servers. We see about 1 million fraudulent installs from there. So I'll explain what's a fraudulent installs and what we consider a fraudulent installs. But if we look in here, when you see an advertisement on Candy Crush, Instagram, Facebook, whatever, of an app, and you actually click on that app, click on that advertisement to see if there's something that you actually like, and you try to install it, this is the user journey that you're going through. And this is how the network provider can actually get the money, the one that posted the advertisement, and the person who's publishing it, the app, Instagram or Candy Crush or whatever, can actually get their money. This is the user journey that they're going through. And they use our software and the software of attribution providers in the industry so that they can know how the user journey looks like and who to attribute, which network. And mobile marketers, that's a term, they spend quite a few amount of money about this thing. We see per day $2 million fraudulent installs going to fraudsters, and we're trying to stop it. That's the job of a mobile attribution provider. That's the job of the people in our industry. This is the user journey that they go through. You see an ad, we call it impression, which is basically the small banner that you see on Instagram or Facebook or whatever. You click on it, and then you redirect it to the App Store. So assuming we have app Y that you see, that's a very cool desk cleaner, flashlight, mobile optimization, battery saver app, whatever. You click on it, you get redirected to your corresponding Play Store or App Store, depending on Android or Apple, and then you install the app. The app is installed on your device, and then from there, our library works. Our library is integrated into apps. We're right now integrated, from what I understand, into 25,000 apps on the App Store. I'm pretty sure marketing team, if they hear this, they're going to kill me because the number is a little bit lower or a little bit higher. I don't know. So, sorry, Andreas. But so install finishes on the device. We fire a request to our servers, and we let the network and the attributors and the publishers know that an install has happened on this device by this app using this impression. And everybody gets money, everybody is happy. This is how mobile attribution works. Now, when there is an industry that you can get over $2 million per day from fraudulent installs, you're going to spend a lot of time trying to think about how to circumvent it. So we have what's called click injection. That's one of the first things that we saw as mobile attribution providers, one of the first fraud schemes. This actually came back from the browser days. Back when you see a toolbar, ask toolbar or whatever, that basically when you click on an Amazon download link, it's going to send the request that, hey, this person clicked on this Amazon download link coming from us. And then they get money for it, and that's considered to be, I think the term is spyware, but I could be confused about the terminology. And it's been ported to mobile. That's how click injection works. The first version of click injection used something in Android. I'm specifically going to talk about Android in this presentation, although we do see iOS click injections just as much, but it's a little bit of a different methodology. So how does click injection, the first version, work? We, in Android development platform, we have in the ecosystem, there's something called broadcasts. It's basically, for the software engineering folks, it's a messaging messenger pattern. Basically, the operating system will send a broadcast, and whoever is listening for it will see it and will be able to react upon it. And this is what's called a broadcast. There is a broadcast in the Android ecosystem called package edited broadcast. Basically, what happens in here is that whenever a package has been edited, a package means an app, by the way. When an app has been edited, the system will be able to send a broadcast to notify any app that is listening for apps that is being installed. For example, I'm app Y and app X has been installed. As soon as app X is installed, I will be able to know about it. How? This is how the Android ecosystem works. If you're listening for it, you can sniff it. And sniffing is a bit of an intrusive term. That's actually a very legal thing, technically speaking. It's a broadcast, and this is a page from developer.android.com. And this is how the first version of click injection was being abused. Yeah. Oh, I should have had like a small prompt in there. Oh, never mind. You see, right on the blue box in the bottom right corner, when the install has finished, there is a small time gap between the install finishing and the user actually pressing on the app and opening it. In that time, if an app has been sniffing that traffic, that broadcast, they can know before the app has opened that an app has installed, and they can start firing off clicks. They can say that, hey, I am network X, and I am this user has installed this app using this device information, and they can collect all the device information that we collect to send an authentic install. And they collect it and they send it to their servers, and people get paid for it. That's the first version of click injection. It's a little bit of a weird quirk. I wouldn't even say it's an exploit. It's a quirk. It's a weird abusage of something very technically legal. And most malware is actually abusing already existing API. If there's any folks in here who know about 132 API, it's basically not all of the time using any exploits. It's more or less just using what's already in the ecosystem itself and trying to use it for its own advantages. So we have in here abusing the package edited broadcast. We solved this thing very easily. This was in API level 9, and this was, I think, 2012, if I'm not mistaken. This was solved very fast. Basically, it sends, you can get the first install time from the app. So when the user opens the app, doesn't matter whatever it is we saw before, until we get something that resembles the first install time, which is the time that the device has received this app and it is existing right now in the user's device. We can get that from the app itself. This parameter wasn't existing before. The app didn't know when it was installed. Right now it knows it, and this is how we solved it. We basically are sending it, and we can make a comparison because there is a very large chain of broadcasts for every advertisement that you click through. When you click through an advertisement, it doesn't go directly to our servers. You go through network A, network B, network C, network D. There is a very long chain of timestamps. And afterwards, we can compare those timestamps and see if they correlate. And we solved this problem a long time ago with this first install time. This is by Google, provided by Google, not made by us. So we can't take credit for it, but it's a problem that's been solved. And yeah, so right now, more or less, my entire talk is going to be focused on the second version of click injection, which in my opinion is much more interesting. It actually can use what we, in the security folk, you can't really say it's an exploit. There is no 0 day, there is nothing like that, but we actually call it an exploit just because it's a rigorous abuse of the Android ecosystem, which we're going to see right now. It's basically changing the timestamp that's been sent. You can correlate all that chain of networks that I just talked about by using a different timestamp, which is the time that the download has started, not the install has started. And that's not a problem with an Android ecosystem. I want to say it's a weird glitch that's not documented, but if you're knowledgeable enough in the Android ecosystem, you'll be able to get it. And this is what the app that I will be going through the analysis for is using. And there has actually been a small typo that I've written. It was my mistake, not DefCamp's. The app has over 100 million downloads on Google Play Store, not 10 million. So it's something that's being used currently. The app is still active. I will go through the analysis later, and there is more than one of them. So this is something that is quite big, and we've seen it a lot. Basically, they just changed the timestamp. So right now, instead of having the timestamp of the download installing, they have the timestamp when the download has started, and they can use that to attribute. I've gave this talk before in a software engineering conference, and nobody asked this question, but I'm guessing here there's more security folk and attackers than software engineers. We're not accounting for the attack vector that somebody will use a bot or a Python script or whatever to launch these installs. That's a different attack vector. Right now, we're accounting in this presentation only for the usage of an actual app, a malicious app that's sniffing data from the background. And this is the exploit that they're using. I'm using the term exploit in here very softly. So it's not an actual CVE. There is no direction for that. So, okay, and basically just using a different timestamp, and we had to do something about it. So if anybody in here is a movie fan, this is actually a quote from a different movie, not Pulp Fiction, but whatever. So Snakes on a Plane for anybody. Amazing movie. All right, so for legal purposes, we are not criminal prosecutors. We can't disclose the name of the app. We can't disclose the nature of the app, but we can name it App X for the reasons of this analysis. And this is a heavily obfuscated version of App X, as you can see in here. It's still being updated. This is a screenshot taken from, I think, 4 weeks ago. But it was updated recently, like the last week of it. As you can see in here, 100 million downloads. This is Google Play Store, if anybody can't recognize it. And yeah, it's a utility app. That means that it is one of those apps that tells you it's saving up your, cleaning up your, decluttering, I think the term that they use, your memory space, or saving your battery, or optimizing your network usage. Any of those utility apps. Just for now, never use any of those. Just please try to put your trust into Apple and Google that they will declutter your memory and save up your battery. Never install this stuff. It actually does what it says it does. It does monitor battery usage. It doesn't do anything with it. It does declutter your memory space. It does what it says it's doing, but that's like the 5% of the 95% that's actually doing. After you reverse the app, you can see it. And there's authentic reviews in here, 13 million reviews. You can see them. More or less, they're written by real humans, as far as I'm concerned, because they sound pretty okay. Let's go through the analysis. So right now we're going to talk a little bit more technical through reverse engineering methodology and how to reverse a mobile app, specifically Android. So to start with this thing, I need to start with a theory. I need to know what am I looking for. I'm not gonna stick it to Radare or IDA Pro and just hope for the best. You can't do that. You're just gonna be faced with a million other libraries that you're gonna have to go through. You're gonna be faced with obfuscation. Yes, they actually do have their own obfuscator, which we're going to see right now. And you can't do proper analysis like that. You need a theory. You need to know what you're looking for, get it, get out, done. And this app is performing a new way of conducting click injections. It's a pretty good theory we can work with. Let me see if I'm good in time. Yeah. So, first of all, static properties. We're going through 3 steps. There should have been a slide in here about the steps that we're going through. We're going to go through 3 steps. Static properties, behavioral analysis, and static analysis afterwards. I'll explain the steps in each one of them, but for now, let's stick with the first step. The findings are in purple if you can see them. The font should have been a different font, but it doesn't matter. So first of all, before we start with the static properties, you need to know like a small basic premiere about Android apps. Android apps use something called permissions, and this is how they inform the user, you, the person who downloaded the app, that this app is going to do X, Y, and Z. It is allowed to do X, Y, and Z. It's not allowed to do anything else. If it's going to do something else, that's considered to be an exploit, actually. If the app can do something that is not already mentioned in the permissions, if the app can make a phone call for you, and it's not mentioned in here, that's more or less an exploit. We're not going to talk about this. We're going to talk about the stuff that is legal, the stuff that the app can do. For example, Firefox can identify your app history, identity, location, photos, and media, whatever. If Firefox can do this, that's logical, reasonable. If your camera app has access to your camera, that's okay. If utility app has access to your contacts list, that's questionable. So that's basic user hygiene. AppX permissions. You are not actually meant to read this thing too much, so please excuse the seriously small font. So, but these are the permissions that it's using, and to the left-hand side, you're going to see a small summary. It's allowed to extract device data. It's allowed to restart itself upon reboot. It's allowed to actually attach itself again, rerun itself without your permission as soon as you reboot the device. It is allowed to monitor and kill running processes. The killing part is not something I'm going to be concerned about because that's if you're downloading a task manager app, it will have to kill other processes. The thing I'm concerned about is the monitoring. Why is it monitoring other apps that I'm already running? So that's already a red flag. By the way, right now I'm going with the assumption that I know nothing about the app. I'm just going with a theory. I'm going to build it from the ground up using those steps and see if that theory still holds up after the findings. Right now, I try to start with a clean slate. All I know right now about AppX is those three things. And we're going to keep building upon it. Broadcast receivers. You remember the first, second slide that I had about the package edited broadcast. This one can actually listen to package edited broadcasts. Now, that issue has already been solved by the first install time parameter, so that's not something I'm very concerned about. But it's still something that is weird that it's there. Not every attribution provider collects first install time. We do. It just does. Our company does. A lot of the competitors do. There's a lot of open source analytics providers that basically post data to your servers that don't do this. So that's something that could still be used. It's kind of like when Mr. Mike Spencer was mentioning about the Wi-Fi cactus. The first thought that came to my mind was about WEP. What's the percentage of WEP wireless networks? For those of you who don't know, WEP is the least secure wireless authentication system. I think authentication system is proper to say, that has ever been created. It's insecure from day one. So if your wireless network is having WEP, run away. Hard-coded databases. This is a big red flag for me. There is inside the app an SQLite database that has 200 app names in it, hard-coded in it. Why is it there? Of course, it's obfuscated, it's redacted, I believe, or censored, I believe the proper word is. But these are mostly games, mostly paid games that have high advertisement campaigns. And there is a list of 200 app names that are hard-coded in there. And it gets better because there is a text file that has a list of 3,600 app names. All recent, all still active on the App Store. And I checked a small revision history of this app. This list keeps getting updated and updated every day. Every update, I mean. So it's mostly games, apps, paid apps that have heavy ad campaigns. It's hard-coded in this app, in this sniffer app. Okay, so right now we're done with the step one. We know that that AppX is capable of extracting device data, restarting itself upon boot, monitoring and killing other processes, and it has a huge list of app names that it shouldn't have anything to do with it. Step two, behavioral analysis. This is basically more or less the same as when you're analyzing malware. You need to run the app in a small sandbox, and you need to see what's going in and what's going out. You can consider it to be a small black box that you don't need to know how the engineering works inside it now. Right now, you just need to know what is happening in it, what's happening out. If you poke it from here, how it's going to react. What's going to happen in the system that it's running in when you install another app? What's going to happen? So we need a plan. We need to lay out all of this in steps, and we need to test it before we move forward. So we need a great plan, and I hope everybody gets this reference. So go to the Winchester, have a pint, and wait for this whole thing to blow over. So yeah, Shaun of the Dead, amazing movie. So, all right, so we need this plan. We need to answer those three questions. What happens when we open the app? What happens when we install/uninstall other apps? I am actually interested on what happens when you uninstall an app. There is also a broadcast that gets thrown into the Android ecosystem that other apps can listen to when you uninstall an app. Most importantly, what happens when you install an app through Google's Play Store? Because our initial theory is that this app is conducting a new way of taking a timestamp that could be used for click injections. So the last question is the most important one for me. So setup. This is very basic setup. The image should have been a little bit bigger, but pardon me for that. When you export things from Keynote to PDF, things just go hiatus. So basically, on the left-hand side, I'm running Burp with a small Android emulator running on my computer. But the Android emulator is throwing everything into Burp, and I have an SSL certificate from Burp installed into my emulator. Shouldn't be a problem. Most apps right now have this thing called SSL pinning, which basically means that if the certificate authority that's the receiving request, if it came from a certificate authority that it doesn't already recognize, it's going to throw a red flag. Now, that's not something I'm really concerned about, more or less because most apps do have that, but this one I checked already with strings, and it doesn't have that specific thing. Super quick pro tip, if you want to check if an app has SSL pinning, just search for strings for X509 for Android. That's, if an app is doing SSL pinning, it has to have that string. Right now, I didn't see that in it, so I didn't need to bother too much. So when you open the AppX, this is the first request that fires from AppX to an unknown server, to a foreign server, and this is the parameters that it's sending. It's a little bit keyworded. Model is understandable, VTK, LS, AID. Let me summarize it for you. This is the same stuff that we use as mobile attribution providers when we want to say that an app has authentically been installed on a user device. This is exactly the stuff that we're sending. We're sending the hardware name. We are very much privacy compliant company, so we can't send anything that is like a MAC address or Wi-Fi SSID point or something like, or GPS coordinates. We can't do that. This is the stuff that we're sending. This is the stuff that the app is collecting right now to store it on a small database with this request. And there is the last parameter at the bottom. That's what's called a GPS ADID. It stands for Google Play Service ID, which basically is the ID that attribution providers are legally allowed to collect to identify a user device. That's from using Google Play Analytics. And you can opt out of that collection. Unfortunately, this app, even if you opted out, it's still going to generate one for you and send it to their servers. So when you open AppX, it has a long-running background process in the form of a notification toolbar. This is two examples of a notification toolbar, just so that you can have a picture. So we have in here Spotify, and we have in the other one, I think this is Yahoo Weather. And please don't take this slide and say that I'm saying shit about Spotify and Yahoo Weather. I love these people. I have them in there. I love you. So AppX is sending device and analytics information over HTTP. When you uninstall an app, that's the second question that we need to answer. When you uninstall an app, what happens? There is immediately coming from AppX. When I install any app, if I have installed Candy Crush, and Candy Crush is on the name of the 3,600 apps that are hard-coded in the app, if it found it, it will send a request to this server with my Gmail account, with the properties and the name of the app that has been uninstalled. Why is it doing this? In my opinion, this is for what's called reattribution campaigns. Reattribution campaigns in one-liner, it's basically when you uninstall an app and the advertisement company has to find a way to incentivize you to install it again. So they make a reattribution campaign and you can reinstall it again. As you can see, it's actually quite a complicated system, quite a complicated setup that I have here. So the most important question that I wanted to answer from this behavioral analysis, which is what happens when you install an app through Google Play. Now, I installed an app, I think I have a screenshot of Subway Surfers and Snapchat, both of them were on the list. When you click the green install button, which is here in Google Play, when you click on it, immediately there is a request that fires from AppX, multiple requests actually. As you can see in here, there are about 11 in the first screenshot from the top corner, and continuing on below, there's quite a few requests going to mostly to mobile network servers, but mostly to their own servers. They have a very specific API key that they use, and you can identify it with it. All of these requests happen as soon as you click the download button. How can the app know that a download has started? That's the question that we're trying to answer in this analysis. And we know for a fact right now that, as you can see maybe in some of the keywords in here, add union, Mobi, keywords that all indicate analytics and network servers. Add tracking.com, stuff like that. And this is a small zoom in of the most important request that I found, which is for an API, for an endpoint called getDLAdd. And I tried to redact most of the important information, but if you look here, this is the same request as this one, just a little bit closer. You can see the last entry on this one, com.kilo.subwaysurf. Right now, I have evidence that whenever I install an app, there is a request that's being sent, multiple requests, but this is the most important one, coming from my app with all my information that is needed to have an authentic install by us, by an attribution provider, and it's going to a foreign server. The foreign server can right now conduct any sort of can conduct any clicks that they want using this information. Whichever network wins, whichever network pays the most money for it, they can do this. And they have 100 million plus downloads. They really have a lot of reach, this app. And this is just one of. So now this is evidence that this app is throwing all the information that is needed for a click injection. If I want to continue and make an entire analysis, I actually have to monitor the requests that are coming from from servers to my app, from foreign servers to our own servers, and to see if this app, if this ID has actually been caught, just to complete the full circle. Right now, I know that these installs are this data is being sent to their servers. I don't know if it's coming to mine. From our analysis, we were able to identify this happening in here, but unfortunately, I don't have it in this presentation. I do have a lot of requests being fired to other mobile networks, not their own. So, findings. This is a summary of what we just talked about. The app is conscious, loosely conscious, of app install and app uninstall. It has a long-running background process in the form of a notification toolbar, and it is capable of sending all the details of a download in progress before the download has finished. All right, this is the final step of our presentation, the static analysis part. How do we know what we know, and what do we do about it? So basically, we need to answer a lot of questions in here on the left-hand side. What's the communication happening between the SQLite database and the text file? Because there's two databases, if you remember. There's one a TXT file, and there is an SQLite database. There is another SQLite database that's called accessibility. It's not in the presentation, but I need to know how the interactions work. I need to know which package name is being used for what purpose. This is quite a long list of analysis, and I can't go through it in the entire presentation, but basically the most important one that we need to answer is that how is it collecting that download in progress? Where is it collecting it? There is no broadcast that I know of in the Android ecosystem that will tell you, hey, Google Play is downloading an app. How about you check it out? From what I understand, there's none like this. So there must be a way that they're doing it. And this is what we're trying to find with the static analysis. We're going to go through the code, decompile the code, and actually know what's going to happen with it. And this is the stuff that we're going to look for. Any HTTP related stuff, Google Play related keywords. I know for a fact that com.play.vending is the package name for Google Play. So that's the package name that Google recognizes that this app is called Google Play. I can search for that keyword. There is what's called content providers, which I'm going to provide a small premiere on in the next slide. And I need to search for possible exploits. There is quite a few exploits. If anybody has ever rooted an Android phone, you already know about this. I have Lineage OS installed on mine, so I know quite a bit about this. It just broke this morning. It actually clock doesn't work anymore, so just really be careful about installing custom ROMs. So there could be C or C++ code in there. It's called Android NDK, Native Development Kit. App X is observing a content provider. That's the first thing that I found. Basically, before I explain this slide, let me go one slide above. Android content providers. A very quick one-liner about it is that it's an abstract wrapper for SQLite databases, for internet archives, for files, for anything that you want. If you want to access any sort of data, you're going to use a content provider in the Android development world. And it's an abstract layer, so you don't have to worry about SQLite databases or text files. You don't have to worry about accessing internet requests or just plain old TXT files, or even, I think they added support for XML recently, but I can't be sure. JSON, you can also use it for content providers. So basically, it's an abstract wrapper to access things. So if you are looking for an app and you are analyzing it, the first thing that you need to look for is a content provider. How is it getting its data? I saw in here that there is a content provider. If you see it, the yellow coloring on the bottom right one, it's called content : downloads. That's a content provider, which I'll be talking about in the next slide, but it's accessing it right here. Weirdly enough, in a class called download monitor. When you decompile an app, not every class is deobfuscated. Not every class is obfuscated. Sometimes the Android system actually needs to know about the file names. This one is called download monitor. So, what is being observed? This is not an official naming. I named it by myself. The temp downloads content provider. Basically, whenever Google Play makes a download, it saves the download itself into a temporary directory, collects all the data, collects all the packets, assembles it, and then it stores it into another content provider. This is the temporary one. When Google Play starts the download of an app, this is where it puts the downloaded files, the packets. And it has in here the column names, as you can see. And column names include something like, this is a SQLite database with a content provider wrapper. So in here you can see ID, entity, MIME type, visibility, destination. The most important one is the second line, the first word, package. That actually means the package name. That's the name of the app. And from what we saw in the request, that's the only thing that my sniffer app, App X, needs to know to be able to launch click injections. That and the current timestamp that it was installed at. Okay, so right now, this is the thing that we saw. Step number one, there is a download contents provider, and we have a small function in here in that download monitor class in here, and it's called observe my download. Now, let me just no, I don't have that slide. Forgive me. So in this function, observe my download, it has a link to that content : // the temporary file, and it can observe it. It can observe what's happening in it. It can observe when a thing happened on it. And there is a small interface callback in here for software engineering folks. It's called a public void on change. This gets invoked. This function gets invoked whenever there is a download in progress in that content provider. Okay, step number two. When a change occurs, a query to another public content provider is triggered. As I mentioned before, Google Play works in a funky way, but this is how the download works. It collects all the packets in a content provider, a temporary one. And then after that, after the download has concluded, the progress bar is done, you can see the open icon instead of the install icon. It actually copies all those packets into another content provider, and it stores it there. The thing is, only Google Play has write access to it, but the temporary content provider, everybody has read access to it. And in here, this is the public downloads content provider. This is where the thing gets assembled. and everybody has read access to it. They can know when the download has done, and they can actually query for the package name and the timestamp of when the download has finalized. And I see that my AppX through the analysis has access and has references to two of them. As you can see in here, getContentResolver.query, and this is the URI. So you are not expected to read this big blob of code, but if you can see in here, if you can go to the line number 99, you will see package name, which is the keyword, the gold, the egg that I'm looking for. It's querying for the entire row, and it's actually getting the package name that we need from it. It's getting the URI, and we in here see a reference that if it's coming from com.android.vending. Before I mentioned com.android.vending is the name of the Google Play package. It's the internal code name for the Google Play app. And we see there is a very complicated process that AppX is going through to go through all those content providers to get the entire full picture at the end. And right now, that's it. Analysis concluded. We know what's happening when an app is being installed. We know what's happening when with the list of 3,700 apps. And we know that this one is sniffing, I believe is a proper word to say it, sniffing the content provider for Google Play's temporary downloads directory. And we're done. So, confirmed findings. That's, I believe we have 2 more slides, and then I'm ready to answer any questions that you guys need. How am I on time?
We're doing good.
Thank you. So, all right. This is the confirmed findings. I just summarized them for you. The last one is very important. It fires a request to a server that includes the timestamp, the package name, and all the information that is needed for an authentic download that occurs from a server into our servers, into the attribution provider. And then the attribution provider will be able to okay, we see that you have all the corresponding information. We're going to attribute this download into network X, network Y, network Z, whichever hierarchy, a chain of networks that came through it. And we wouldn't be able to do anything about it, because I say wouldn't, not couldn't, because I'm going to show a mitigation afterwards. But we were not able to do anything about it because we didn't have the proper timestamp. We needed what the malicious creators of AppX, we needed to know what they knew, and we needed to get it faster than they did, and we needed to get it in a way that doesn't allow them to get it after us. And we're going to talk about the mitigations right now, right in this step. Theory confirmed. The app is conducting a new way of click injections. And the mitigations. The mitigation is actually quite simple. It's more or less the same mitigation as the V1 of click injection, which is having the timestamp. Right now, this is in collaboration with Google. This is what's called the Play Install Refer API. It's an API because Google usually doesn't integrate anything that happens from a report that came from us or any security company, that they just integrate it immediately into the Android ecosystem. They usually put it into its own separate plugin, see how it works, and then they integrate it. More or less like a beta test, but this one is finalized. And this is called Play Store Refer API. It's an extra plugin for Android developers in there. It's a Gradle dependency that you can add, and you will get, once we instigated the library that is inside the app, the attribution provider library, we will be able to get the download time immediately, the one that it started, from the Google Play servers, not from the content provider, because apparently what Google told us, the content provider is actually lacking in the timing. So this one is more authentic, faster, and it's very much capable for of us to use it only for the apps that have that's been installed on Google Play. So that's more or less an extra verification too. And yeah, in this Play Store Refer API, we were able to get that timestamp, and right now we send the timestamp with every request, and we still see a lot of apps that don't integrate this, because not every app integrates this. You have to opt in. This is not an opt-out situation. Yeah, this is an opt-in situation, not an opt-out situation. So every app has to integrate it by itself. We can't integrate it for them. And part of this is before the conclusions, part of this talk is that $2 million per day fraudulent installs, over 1 million downloads that are fraudulent installs per day, that's not a small number. And 100 million downloads with 13 million reviews, that's not a small number. So part of this talk is actually more to educate the people and the developers especially to use technologies like this, to follow along with what's happening, because if you're not conscious about this stuff, you're still enabling people to steal traffic, as the name of the title. They will be able to steal traffic, they will be able to fund their operation, and they will be able to get more money out of you. Whether it is you install an ad block or not, because back referring to the browser days, a lot of people said, oh, I'll just install an ad block and this thing's going to go away. This is not going to go away with an ad block. This is going to go away with keeping up with what Google developer folks write on their blog and actually trying to use technologies like this to stop a fraudulent operation that, based on an article on Business Insider I read, by 2025, there will be $50 billion going through fraudulent channels, all coming from advertisement from mobile marketers. $50 billion by 2025 has been collected. The link for that article is on DefCamp blog. You can check it out in there. And that's more or less everything about what I have to say. I just have to add one more thing. The people who were able to get this content provider exploit, as we like to call it internally, they didn't get it because they hacked Google servers or had an inside job or something like that. They just really knew the Android ecosystem. So I'm actually proposing for all security folks in there who know about this stuff, please share it, make it public so that more people you can share the knowledge, we can stop, we can mitigate attacks like this. And if you know something, please speak up. There's a Hacker News article I read a couple of days ago about a VirtualBox guest to host zero-day exploit. I'm sorry if this term is confusing for the non-technical folks. And he actually contacted VirtualBox folks, from what I understand, and they said that they're going to mitigate it later. So he published it on his GitHub account. That was very good. That was really good. He knew about something wrong that could actually impact people, and it could be very problematic for a lot of people, and he published it. Please do that. Make the knowledge public. Make it so that you will benefit the community, you will benefit the people, and you would stop literal money trafficking happening in here. So that's all I have to say. Thank you so much.
Thank you. Thank you so much for the super practical presentation, Abdullah. We're ready for some questions for you. So please put your hands up.
Thank you for your presentation. Scary stuff, actually. How proactive is Google regarding doing this kind of analysis on their most installed applications? Did your findings take them by surprise? Were they aware of it?
I can only comment that there is a direct line between us and Google and Apple, and we and the developers are working very proactively to understand what's happening in here and for both of us to have a healthy communication of what's happening and the environment. So yes, they are aware of it. They are very proactive about it, and this was released very as soon as the findings were found, as soon as the findings were put forth. So they are very active about it. Apple as well. Just one extra thing. I'm not mentioning that Apple iOS is safer or Google Android is weaker. I'm not mentioning that. iOS has its own little bag and Android has its own thing. This talk is more about Android because I felt like it's a little bit easier to explain it rather than try to explain an iOS jailbreak with like a null byte memory leak. So yeah. I hope that answers your question.
Yeah, thank you.
Let's take one from the other side as well, and then we'll get back to you.
I wanted to ask, do you have any advice as a developer for a client with basic knowledge? How can he improve his behavior so he wouldn't run into apps like this?
Get better developers. I'm kind of serious. The developers need to know about the communication channels that Google and Apple try to provide for the developers. One of them is the Android developers blog. And Apple, from what I understand, they release an, I can't remember the name, it's like security dossier for every iOS release that they have. It's really short, it's very practical, it has a lot of pictures, and they release it with every iOS update that they have. It's about 15 to 20 pages of the most important things that a developer needs to know on how to conduct security in their app. OWASP has a chapter called MSTG, OWASP MSTG Mobile Security Testing Guide, which I recommend every developer to check out. It's on GitHub, and they are going to publish a book, hopefully beginning of next year, about mobile security and what developers need to know about cryptography, what developers need to know about secure network requests in their apps and the libraries that they need to use, all of that. Those 3 resources, I highly recommend every developer to know about this and always follow it up with the proper channels. So I hope that answers your question.
Awesome. One more question.
You said that this problem won't go away by installing ad blockers. But in my mind, if I install an ad blocker on my device, every ad provider request just won't go through. So I'm asking, why won't the problem go away?
Okay, I'll answer your question in 2 ways. First of all, the ad block technology right now in mobiles, I don't think it's very strong. At least there could be like an ad blocker on your as an app that will run as a background process. That's the first thing. I don't know of anyone. I know AdBlock Plus or something on browsers on Chrome. I have it installed, it's pretty good. The thing is, the second question, which is more important, do you actually trust those ad blockers? They're basically having a long-running notification, long-running process, and will stop this thing by sniffing your traffic and cutting this thing in the middle.
I would trust an ad blocker if it only changes my host's file to redirect all the ad providers back to my phone. So
that is correct on a browser. Please correct me if I'm wrong, anybody, but from what I understand, in Android, you can't actually just block that. You can't block a host's file or change it without root permissions. So that could be a little bit of a problematic thing for an app. If an app was able to do that, that's perfect. That's really good. It can stop at least the most known ones, which is very good. And yeah, that would be a very good solution to our problem. But in my opinion, that would require, you'd have to think about how to secure the host's file and which permissions to give for the ad blockers, and are they allowed to give it to other apps? And we're going to come back to the same problem in here. So yeah, thank you.
Thank you.
Thank you as well.